Hi ladies, today we're going to look at mass spectrometry. So one of the things that we will come across at the end of this are some mass spectrum. So this is an example of an actual mass spectrum. Of course, when we look at the X and Y axis, well, this diagram doesn't have any, but what we will actually see is a little neater than this, but what is represented by each of these peaks is the mass of what we call a fragment or a molecular fragment. So as we go through this particular module, Unit 2, Module 2, Objective 7.1 to 7.3, hopefully at the end of it, you'd have an understanding of how a spectrum like this comes about. And then we'll have another session where we will look at the actual interpretation of something that looks somewhat like this, of course, simpler. So according to your syllabus, these are the things that you're expected to know. And what we're going to cover today, we're going to cover 7.1 and 7.2. So we're explaining the basic principles of mass spectrometry. We're explaining the significance of the M+1 peak. Now keep in mind, please note that you are expected to know the block diagram, simple schematic for the mass spectrometry process or the separation. So mass spectrometry is, the syllabus has it here as spectroscopy, but it really is spectrometry, and I'll explain why. Mass spectrometry is an analytical tool that separates based on a specific characteristic. So we do need to know what your block diagram is, and in explaining the basic principles, I know when we did IR and UV vis, there were certain questions that you had to answer. It's slightly different with this because this is not a spectroscopic technique. It does not involve light. It involves some other processes. So explaining the basic principles, you will not revisit those questions. It will take you in a slightly different direction. So we're looking at 7.1 and 7.2 in this session. So by the end of the presentation, you should be able to state some applications of the mass spectrometer, identify the simple parts, and this is taking us specifically to that objective 7.1, and explain how the mass spectrometer analyzes an atomic or molecular sample. This is, as I said, explaining the basic principles, explaining the formation of the molecular ion, and then identifying specific parts of the structure. Now, while we're going to talk about the molecular ion today, when we actually analyze some spectra, we're going to look at the other parts, referring to the molecular ion cluster, the M+1, M+2 peak, etc. That comes a little bit later on. These are some other things that we're going to do, but that will not be in today's session. So what is mass spectrometry? So it is a technique that is not using electromagnetic radiation. So your spectroscopy measures light. Spectrometry, you get a measurement, you get a spectrum, but it does not involve light. It involves something else, as we're going to see. So just keep that in mind, and you use the appropriate naming of it. It's not mass spectroscopy, it's mass spectrometry. Now, this is a technique that has many uses, and we will find that oftentimes it is used with something else. So those of you who look at forensic crime dramas, for example, you'd hear them talking about the GC mass spec. One of my favorite shows always refers to the GC mass spec. That would be about NCIS, or you know, if you are a CSI fan, or any of those shows where they actually look at forensic science. It's a very important tool in forensic analysis. But we also use it for structural determination. That's the main purpose of it. It allows us to determine the structure of certain molecular compounds. We also use it for elemental and atomic analysis, and we've seen the data of that. But what we're focusing now is the molecular aspect of it. So it helps us determine the precise molecular and atomic masses. It allows us to characterize the structure of some unknown compounds. So as we speak of the elucidation of structure of organic compounds, it helps us put together the structure so that we can identify what makes up a compound. the fragmentation patterns that will come about also give us useful insight about what the structure actually may be like in terms of primary, secondary, tertiary types of structures. It allows us to identify components of a mixture. And this is a very useful aspect of it. For example, as I said, we look at it as an in tandem technique. So your mass spec is often attached to a gas chromatography apparatus, where the gas chromatography, which you will do with Ms. Smart, the gas chromatography separates the sample, and each of those components of the mixture come out at different times and are measured by the mass spectrometer. And the mass spectrometer, the data from the mass spectrometer allows us to then identify what each of those compounds are. And then if you are doing gas phase reactions, organic chemistry, synthesis or analysis or whatever, this is another use for it. So as I mentioned before, the applications are forensic science. This tends to be one of the more commonly known ones, but it is also used in testing geologic samples, i.e., something that you have a particular element or a particular sample of soil or some unknown, some new compound, some new, as I said, element, because then we look at the atomic analysis, and that will tell you whether your sample has carbon, whether your sample has aluminum, because each of those atomic spectra that come out of atomic spectrometry will have a unique pattern. It is used in drug testing and drug discovery, monitoring of petroleum, chemical, and pharmaceutical, and in just everyday research. More often than not, as I'm repeating to say, it's used alongside another separation technique to then be analyzed in the mass spectra. So the three main components, the three main things that happen in a mass spectrometer are these. We convert the neutral atoms or molecules into ions. So there is the ionization aspect of your sample analysis. And then after these samples are ionized, we separate them based on what is referred to as mass to charge ratio. And this charge is very important because we see that the conversion is forming a charged ion, positively charged ion. And after we've separated it, then we measure the relative abundance. And if you remember looking in Form 3 when we started looking at atoms and relative atomic mass, we did some calculations where we talked about the relative abundance of certain atoms or isotopes in a sample, and this is where that data would have come from. That element would have passed through a mass spectrometer, and you would have gotten the relative abundance of each of the isotopes at that level. At this level, we're looking at the relative abundance of each of the ions or each of the fragments that would have been separated in the mass spectrometer. So we look at that again. Three major things that happen in your mass spectrometer for analysis. We look at the conversion to a charged ion. We look at the separation based on mass to charge ratio, and then we measure the relative abundance. And that relative abundance is what is plotted on your mass spectra. So we have both atomic mass spectra and molecular mass spectra. What we're going to spend most of our time on at this level is the formation of, or the analysis of, molecular mass spectra. So this is just a real life gas chromatography mass spectrometry instrument, your GC mass spec, as you may hear it referred to. Almost every single lab, university, forensic, anybody doing chemistry anywhere, even physics as well, they will have a gas chromatography mass spec instrument. And the different parts of it in the gas chromatography mass spec instrument, you have a component or an area which is your gas chromatography component, and then you have your mass spectrometer. So just remembering what chromatography is, chromatography allows you to separate a sample, and it will pass through the coils with your gas as your mobile phase. And after each of these samples have come out, remember your chromatography will separate it based on solubility, etc. Each of those samples will then pass into the mass spectrometer, where it is separated even further, and then your computer will analyze it and determine what actually was the compound that you got out of the chromatography column at that time. So this is what your GC mass spec looks like. A closer look inside your mass spectrometer shows you this. We have the left side, we're starting off with where the sample gets injected, and then we have a vaporization process, because we're well aware that it is easier to remove electrons from things in the gas phase. If you look back at your atomization energy, enthalpy of atomization, it is always with the gas phase substance. So we vaporize the sample, and then we subject it to an electron beam. And that electron beam we're seeing here in phase 3 is what allows us to ionize the sample, or then generate the positive charge. And after the positive charge is created, it then passes through a particle accelerator, speeds up the particle, and then it passes through a magnet. And that magnet is what is then responsible for the deflection or the separation based on its mass to charge ratio. So if we kind of just go back, your GC mass spec, now it might seem like it needs to be a very big instrument, but really it doesn't, because remember, we're looking at, and oftentimes if you look at these little vials on the side, on the left, on the right side here, and even on the top, which is your left side, it's really microliter volumes of sample that oftentimes gets used in a GC mass spec or in a mass spectrometer in general, very, very small amounts. So that, remember, you know, your particles, a mole, 6.0 by 10 to the 23 particles can be 1 mole, and we really don't need a lot. So don't think that this needs to be any massive instrument. You really, it can be very small. And it's another thing that one of the advantages of this type of technique is that, again, it uses a small amount of sample. However, one of the disadvantages is that your sample is destroyed at the end. So while it only takes a small amount, you cannot reclaim the sample at the end, because the bombarding, etc., will break it up into something different, and it cannot be put back together at the end, or what's the word? You can't get it back, right? So this is a fancy diagram for what inside your mass spectrometer would look like. This is a simple diagram, simple schematic. Again, you could put this on a block diagram, perfectly horizontal. There's no reason for you to actually try to draw this in the curved fashion. This is here for us to understand what can happen. But we have our major parts. And if you think about the 3 things that need to happen, we said that we have conversion, separation, and measurement. And under the conversion, separation, and measurement, each of these things are accounted for here. Your conversion is your ionization chamber. Your separation starts off with the acceleration, and then we have deflection. So that becomes your separation section. And then your detection is the part where we now start to do the measurement. So again, you can create your block diagram with each of these parts, your ionization, your acceleration, your deflection, and your detection. There's absolutely no need for you to try to curve the diagram or even draw it like this. You really just could put together a simple block diagram that looks like this, right? So we have our sample going in, our ionization chamber, our ion accelerator, our magnet, mass analyzer. Some text will give you the magnet and the mass analyzer as the same block, and then your detector. And that then will give you a mass spectrum that will have relative abundance on the y-axis and the mass to charge ratio on the x-axis. So focusing on what actually happens in our mass spectrometer. We have our ionization, our acceleration, our deflection, and our detection. All of this happens in a vacuum at low pressure. And it is important to remember that this happens in a vacuum, because what we need to do is make sure that we don't have any other gas particles that will collide with our sample and perhaps fragment it or change its charge in ways that we do not predict. So we remove any air from the mass spectrometer to ensure that the only gaseous particles that are passing through the mass spectrometer are the ones that are being analyzed. We don't want any oxygen coming out on our sample, on our mass spectrum. We don't want any nitrogen, any carbon, no ambient noise. We want to remove that from our sample as well. So it minimizes collisions, and we also ensure that we don't have any of those things being picked up by the detector. So this is our first part of our mass spectrometer, which is our ionization. These diagrams can be found at chemguide.co.uk with additional explanation if you think that that's something that you need. So a sample goes in at the left, and when the sample goes in, it is passed over what we have as an electrical metal coil. Now, if you remember, electrons on a metal are constantly moving. Your electrons are in constant random motion. With sufficient energy, we can get these electrons to move off of the metal. This is why your metals are shiny, because with sufficient energy applied to the metal, what we are seeing as shininess are the electrons that have absorbed light and then de-excited and giving off light. That's what our shiny metal is. So it's very easy, it's relatively easy to get an electron to jump off of a piece of metal, really, right? It doesn't need a whole lot of heat, it doesn't need a whole lot of energy to do so. So we have an electrical coil, and what that electrical coil is going to do is allow the electrons off of that metal to fly off, if you will. And that's the diagram that's showing you on the bottom left here. That's the filament. And the electrons are going to leave the surface of your coil. On the opposite side of that coil is our electron trap. Now, what is our electron trap designed to do? As the name suggests, it's going to trap the electrons. That electron trap is going to have a positive charge. And because it has a positive charge, it's going to pull the electrons from the coil's surface across to meet it. So what we have here, you could use the analogy of a highway of very fast moving electrons, because they're coming off of the coil and they're coming very quickly across to the electron trap. So they're moving very quickly. The vaporized sample enters this section here, and as it passes through, it's going to have no choice but to cross the highway, right? It will pass through the beam of these electrons. And because these electrons are moving very quickly, you're going to have some of them with sufficient velocity that they then knock an electron off of the sample that you have coming into its path. I'll say that again. We have our heated coil, we have our electron trap on the other side, and these electrons are moving at very high velocity. We have then our sample coming in, and when the sample enters this chamber, the sample particles, the molecules, the atoms, whatever, that pass through the beam of high-speed electrons, they're going to find themselves being bombarded, hit very quickly with high-speed electrons, and those electrons are going to in turn knock another electron off of the molecule or the atom. Remember, the purpose of this section is to ionize our sample. So of course, if you're thinking about an electron getting knocked off by another electron, what we're going to end up with is a positively charged ion. And that positively charged ion is going to find its way through this beam here, as we're seeing positive ions on the right side here, and it's going to find itself passing through this beam. Now on the left side, we're seeing an ion repeller. That ion repeller is there to ensure that the beam of the beam of ions, your now positively charged ions, continue to go in a particular direction. That is out of the ionization chamber. So of course, what charge would you expect the ion repeller to have to make sure that these positive ions now leave the chamber? So this is what happens in your ionization step. You get bombarded by electrons, high-speed electrons, and in this bombardment, the electrons knock off an electron and form what we call a radical cation. So this is just saying exactly what I had said before. Your vaporized sample enters the chamber, electrically heated, etc. Right? So this is for your notes. So when the molecule bombards the electrons, we get what we refer to as our molecular ion. Now, this is not by accident that I have both a positive side and a dot here. Remember, your radical cation. We had looked at the formation of radicals when we have heterolytic fission, homolytic fission, where the bond breaks in such a way as to leave the electron unpaired. So in the ionization chamber, the removal of the electron allows for an unpaired electron to be left behind and a charge, positive charge, to be on the ion. This is the molecular ion, and your molecular ion is the molecule minus an electron, which means that it has the exact mass of the sample that you've put into the substance. So by definition, this is what your molecular ion is. The species formed by the removal of a single electron from a molecule. It is a radical cation, has an odd number of electrons because we've knocked one off, and has a positive charge. So this is the equation for the formation of the molecular ion. There have been questions that have actually asked for this, and so you will find slightly different versions of it, but the general equation is what is shown in the section down at the bottom. But the ionization happens where the molecule, an electron comes in and knocks another one off, so that you have the two electrons leaving, and then you get your radical cation, or as we refer to it as the molecular ion. This molecular ion, as it passes through the mass spectrometer, will undergo further fragmentation, either through bombardment with electrons or through stabilization of charge, and we have tertiary versus secondary, etc. You will get further fragmentation of the radical cation in your mass spectra. So again, if you are asked for the general equation, pick either one of these. Make sure that you are balancing for charge, that meaning your number of electrons are consistently balanced on both sides, as well as your M being whatever molecule it is. Each mass spectrum has a unique pattern. No two compounds, no two molecules, no two atoms have the exact same fragmentation pattern. And that's what makes mass spectrometry so useful, because again, once you get a fragmentation pattern arising, you could very easily identify that compound, its entire structure. So we've mentioned this in terms of getting your ions out. So now that your ions have been formed and they've left the ionization chamber, oh, right, this is what it looks like. This is just your tungsten filament, regular thing. Turn the light on, electrons start to hop off. Once they've left the ionization chamber, they are accelerated by passing them through different voltage or different plates of different voltages. Right? Now, we don't need to understand in any great detail the physics of this, but understand that the speeding up of the particle with the positive charge happens by passing it through successive plates with different voltages, highest to lowest. So now you have a particle that is positively charged, has a radical cation, has an unpaired electron, and is moving at very high velocity. We now get into the curved part where we look at the separation based on deflection or degree of deflection. Deflection happens based on two things: the mass of the ion and the charge of the ion. And if you think about it, remember it's a curved area and we're looking at something turning the corner, if you will, right? What will, if you have two particles having to turn a corner, depending on the speed of the particle, depending on the mass of the particle, the charge, well, if the two of them are traveling at the same speed, really, one could crash and one could make it safely across, depending on the size of the ion or the charge of the ion. So this is what we depend on, and the importance of the mass to charge ratio when we're looking at our deflection. So your mass to charge ratio is simply mass over charge. So something that has a mass to charge ratio of 28, we assume that if it has a charge of 1, then the ion has a mass of 28 atomic mass units. We don't at this level look at things with a higher charge that is beyond our scope at this point. So for the most part, we assume that most of the ions have a charge of 1, so that any mass you see on that x-axis is the mass of the ion that has come out of the sample. So this is what happens when we deflect, right? We have different fragments, multiple fragments. Remember, we had a molecular ion, and that molecular ion can break up into different things. It could remain as the molecular ion. Many things can happen to essentially break the molecule apart in that ionization chamber and as it passes through the acceleration chamber. We have imagine three streams that will pass through the magnet. Now this magnet, we can adjust the electromagnetic field, right? We can adjust the field of the magnet to have different degrees of deflection. So in this one particular stream, at this one particular magnet strength, we're seeing three different types of particles, three different ions are coming through the deflector at the same time. We have stream A in blue, stream B in green, and stream C in red. And based again, as we said, on the mass, we're not going to look at the charge because we're assuming that all of these have the same charge. So in this particular case, we're looking at the mass to charge. The ion stream A is deflected the most and will hit the sides of the deflector. Ion stream C will be the least deflected. And this is based on what we had seen here. Lighter ions are deflected more than heavier ones, etc. Right? What is important is appreciate that all of the ions are not going to reach the detector at the same time. Again, we can change the magnet strength or the magnet field so that at this particular magnet strength, we can get an ion stream B passing through and getting detected. And then I can change my field somewhat, my magnetic field, and I can get ion stream A and ion stream B hitting the walls, and then ion stream C comes out. And then I can change my my magnetic field again, where ion stream A comes out, and then ion stream B and ion stream C get deflected. So at different points in time with different magnetic strengths, we can get the different ion streams coming out of the sample. And it's easier done that way because having all of these streams hitting the detector at the same time can overcomplicate matters, right? So understand that your deflection or your separation happens based on the mass to charge ratio. That's really the key takeaway. So having left the separation area, we now have detection, where only one ion stream, as I said, will move towards the mass analyzer or the detector. The others are picked up by collisions with the wall. It will pick up electrons and then become neutralized, and then it gets sucked out through the vacuum pump. The ones that reach the mass analyzer are detected using what we call, will produce an electric current. The higher the electric current, the larger the abundance of that substance, right? The greater the electric current, that is red, the larger the the larger the abundance of the substance. So very quickly, how does that get red? The ion hits the detector, which is made up of a metal. Once it hits the detector, remember it's positively charged, and we have an electron that will that will pop onto the ion. That electron will leave a space on the metal, and that space will then be taken up by another electron. And the space that was left by that electron will be taken up by another electron. And what does the movement of those electrons produce? The movement of those electrons, the hopping of those electrons, will produce the current. So the more ions that hit the detector, the more current that is produced, and the larger the relative abundance peak that we get. So your mass analyzer will detect the amount of each ion that would have hit the detector, or will measure, and that will be translated to your mass spectrum. And again, your mass spectrum, we have a mass relative abundance on the Y, and we have our mass to charge ratio, M/Z, on the X. And each of these peaks that you will see will be a particular isotope if it was atomic, or it will be a particular fragment if it is a molecular separation. So we're looking at our molecular ion and our fragmentation in the mass spectrometer. When the molecular ion is formed, we see that we also get an M+1 peak. The M+1 peak is what we refer to as our molecular ion +1, and that is the result of our carbon-13 isotope. I'll go over this later on, but I'm just kind of introducing the idea here to you. We also have our base peak. Your mass spectrum will also have your base peak, which is the most abundant ion in the mass spectrum. And that is usually produced from the most stable fragment in the sample. The most stable fragment that comes out of your sample would be the one that creates the base peak. And that's what this part of it looks like this, your M peak and your M+1 peak. I'm actually going into it. This is your molecular ion cluster, your M, mass to charge, and your M+1 because of the carbon-13 isotope. And then this is a simplified mass spectrum of pentane, where we see 72 being the mass, your molecular ion, because it is the mass of the the mass of pentane. This has no M+1 peak because of the relative abundance. In this case, it's going to have a very low relative abundance. So this just introduces you very briefly to this last area here in terms of how we analyze, how your mass spectrum looks. We will revisit this when we spend a little bit more time looking at actually analyzing a mass spectrum, but please be aware of it, make a note of it, so that when next I see you and we actually meet face to face, you have an idea of what these things mean and how we can then start to apply it. So that's it. We have looked at the basics of your, we've looked at your basic principles of mass spectrometry. We've looked at our simple schematic diagram. We've briefly explained the significance of the M+1 peak in mass spectra, but hopefully with a little bit more practice, you will understand what that looks like. So we'll wrap it up here, and I'll see you all next time.